First, let's consider the power at resonance. So we know that the power that's delivered by the battery is equal to the potential, V of t, times the current. Now, at resonance, we've already seen that the phase is 0. I haven't written down the expression for the phase at the moment. And so what we have here is, at resonance, power max delivered by the battery is V naught I naught sine squared of omega t. Now, that's oscillating in time. So when we look at this function, and if we plot that out, it's going like sine squared. So we'll just plot a sine squared function. And here, the maximum value is when sine is 1. So that's V naught times I naught. Now, one of the interesting things about this sine squared function is that when we look at one period, and our one period, remember, because it's sine squared, our one period is right here. So this is a period, t, of oscillation. That's when omega t equals 2 pi. That if we just look at this heuristically, we see that the sine function is both spending, if this is 1/2 the maximum value, then what we have here is we can divide this up and see that the area under this curve, and I didn't draw this in a spectacular way, but if we integrated sine squared of omega t dt over one period and divided by the period, then that comes out, we expect from just looking at this diagram, that that will be half the value that sine squared can take as its maximum value, 1. Now, this is what we call time averaging a sine squared function. We're averaging sine squared over one period. We have to divide by the period. So sometimes we write in the notation a bracket sine squared omega t to indicate the bracket indicates a time average. Now, we can prove this result by using some of our trigonometric identities, that 1 over t, 0 to t sine squared of omega t is equal to 1/2 times 1 minus cosine of 2 omega t. That's a trig identity. And when you integrate the half over one period, that's just 1/2 times t divided by t. So we get a half. And now when we integrate the cosine, so let's put a minus 1 over 2t. Now, the integral of the cosine here is sine of 2 omega t. And we have to divide by, again, 2 omega. You can check this by differentiating sine of 2 omega t. You get 2 omega times cosine 2 omega t. There's the minus sign, the half, the t. And we're evaluating from 0 to t. But remember, omega t equals 2 pi. If you put in 4 omega t, so if we put in, for our time, 2 omega t, that's equal to 4 pi. And sine of 4 pi is 0, minus sine of 0 is 0. So this term is actually 0. And that justifies what we said about our time average. So now let's time average the power delivered, the maximum power, time averaged, delivered at resonance. And so what we're getting here is simply the sine squared is a factor 1/2. So we have 1/2 V naught I naught. Now, there's a notation that's often used, which is to write root mean square amplitudes for the voltage as 1 over root 2, and a root mean square amplitude for the current as I naught over root 2. And so when you see, if we multiply these two terms together, we get that factor of half. And so our bottom line, we can say it this way, is that the maximum time average power delivered at resonance by the battery is just equal to V root mean square times I root mean square. And this reminds us of just how power is delivered by a battery in a DC circuit, voltage times current.